If the Earth had a birth certificate, it would show that our planet is 4.6 billion years old. The first life forms appeared some 4 billion years ago, although there would be a wait of 2.5 billion years before the appearance of the first multicellular organisms related to animals, our oldest ancestors, found in the fossil record. Taking these timescales into account, it is logical to think that the evolution of life was a slow and linear process, where some species succeeded others or formed branches over long intervals. Paleontological research tells us that this was not the case. Short episodes of intense evolutionary change alternated with long periods of relative stability. These were genuine revolutions, one science is trying to find the causes for. The greatest of these revolutions took place about 542 million years ago. It is known as the Cambrian explosion of life, the biological Big Bang. The Cambrian is the first period of the Paleozoic era, the era of ancient fauna. It began 542 million years ago, when plants and animals lived exclusively in the sea. Those seas bathed continents far different from those we know today. If we travel back in time, we can see that at the beginning of the Cambrian period, there was a large continent called Gondwana, which covered most of the southern hemisphere. Other smaller continents were Laurentia, present-day North America, Siberia and Baltica, the Eastern Europe of today. They were all formed from the breaking up of a single supercontinent we know as Rodinia or Pangaea II, which existed until about 650 million years ago in a little-known time we generally call the Precambrian. For something like 3.5 billion years, ecosystems were extremely simple and poor in biodiversity. Bacteria, algae, and finally worm-like soft-bodied animals populated seas where free oxygen was very scarce.
One of the great discoveries, I think, of 20th century science is recognition that there was life on this planet almost as early as it could have been physically sustained. The oldest sedimentary rocks on this planet have evidence of life in them, 3.5 billion years old. So there's a huge history to life on Earth. What I think is fascinating about that history is life appeared very, very early on, but we don't get animals, we don't get large organisms until we're up in the Phanerozoic. That's what the Phanerozoic means, is the age of visible life. We have life on Earth at 3.5 billion years, but there's 3 billion years go by when we simply looking at microbial types of organisms. There's nothing large, there's nothing complex. It's all very simple.
About 575 million years ago, towards the end of the Precambrian, the Deeakron fauna appeared. The animals in this fauna were small, medium and large-sized soft-bodied organisms, reaching up to 1 metre in length, and they lived in shallow seas all over the world. Their identity is the subject of intense debate in the scientific community. Were they animals or large single-celled organisms? Were they ancestors of today's living beings? Or, on the contrary, were they a failed experiment of evolution? Research points to the fact that most of them disappeared without descent in what was one of the first great extinctions in the history of life. Why did the Deeakron fauna die out? This was mostly the work of the new animal groups that appeared in large numbers and with great diversity in the Cambrian explosion. Life on Earth changed.
The planet was in a great state of flux. It was undergoing a major change. From a planet populated by microorganisms, Earth became a planet swarming with the first animal forms. Some of them were already similar to the large groups or phyla of present-day animals. Others were completely new. But by the end of the Cambrian, many would disappear forever from the face of the Earth.
With the explosion of biodiversity, which would last some 20 million years, an as yet unheard of ecological phenomenon would arise: predation. This was possible as the result of the appearance and development of the skeleton. Hard parts could be used for both attacking prey and in defence from potential enemies.
The appearance of large predators also determined the evolution of life. We know the Cambrian particularly as the time when a large number of animals appeared with skeletons. In other words, animals with mineralized body parts, like the shell of a mollusk or trilobite, and even the plate-covered integument of a worm. These skeletons initially played the part of protective armor against predators. Some animals adopted this armor, while others would be obliged to seek refuge inside the sea bed. This led to the appearance of many traces, of feeding traces, escape traces. Animals tried to avoid predators at all cost. And the more ways of doing this that were discovered, the more new morphologies that appeared. So in only a few million years, life became 1,000 times more diverse than it was in the pre-Cambrian.
There are several different interpretations of whether this was really an explosion of life, a very rapid event taking place in the Cambrian period, or whether it had a longer history going farther back into pre-Cambrian times. And many authorities are of the opinion that perhaps the origin of many of these animal groups is to be found perhaps several 100 million years earlier in the pre-Cambrian, but because they didn't have readily fossilizable parts, we get no trace of their remains preserved.
Bearing in mind the diverse opinions, what factors would contribute to the explosive evolution phenomenon observed in the fossil record? The simultaneous appearance of skeletons in different groups points to the action of important new environmental events. Geological data indicate that on the threshold of the Cambrian, there was a significant increase in substances dissolved in the seawater, such as phosphate and carbon dioxide resulting from intense volcanism and dissolved free oxygen.
Oxygen became the major determining factor for radical change. During the Precambrian, there was a continual increase in oxygen levels, which began to accumulate some 2.3 billion years ago. At the beginning of the Cambrian, these would have been about 10% less than today's levels. Oxygen meant more efficient metabolism for organisms with enzymes that could enable them to live with this new element. It also meant extinction for other organisms, or their being reduced to very special environments. The benign climate was a factor that helped, but it wasn't determining. Perhaps the most important factor was the level of oxygen. One should remember that atmospheric oxygen is released by the action of living beings. That is, once life appeared on the planet, this is what began to produce free oxygen. And this was accumulated over time, until, in the period preceding the Cambrian, its level was not far from what it is today. With oxygen levels similar to those we have today, the conditions were given for life, particularly animal life, to start to evolve greatly and experiment with its forms. In other words, this couldn't have happened 100 million years before the start of the Cambrian Revolution, given that levels of oxygen in the atmosphere and in the sea were not high enough.
That's an interesting possibility. Other suggestions, there is one of the planet's most intense intervals of glaciation happened right at the end of the Precambrian, so-called snowball Earth situation, and people like to point at that and notice that animals appear very shortly after the retreat of those glaciations, and that may have something to do with the origin of animals and the Cambrian explosion. To my mind, it's not very helpful. I don't understand why freezing the planet over would induce an interesting new kind of evolutionary phenomenon. To my mind, the oxygen hypothesis is an interesting one, but I'm not sure that even that is a necessary constraint.
For one reason or another, or through the combination of several, life found its space and was expressed in thousands of different ways. Researchers are on the trail of that remote past when the foundations of modern ecosystems were laid. Where does this trail begin? Through colossal orogenic forces, the geology of the planet brought to light different Cambrian sites with exceptionally preserved fossils on 4 continents. One of the first finds was made on the westernmost coast of Wales, in the United Kingdom, on this rock wall in St David's.
The Cambrian period takes its name from the Roman name for Wales, Cambria, which is called in Welsh Cymru, which is rather similar. And the name was coined by Professor Adam Sedgwick of the University of Cambridge back in the year 1835. And he was the first person to investigate these very old rocks cropping out in North and also in South Wales.
And it is here, on the western tip of Cambria, or Wales, that one can find the great protagonists of the Cambrian, the trilobites. To date, some 30,000 different species of trilobites have been classified, although estimates of the total number could reach 100,000 species of this type of animal.
Trilobites are extinct primitive arthropods from the Paleozoic era. Their bodies are divided lengthways into a head or cephalon, numerous thoracic segments, and a tail or pygidium. Transversally, their bodies were further divided into 3 lobes, which explains the name trilobite. Trilobites were the emblematic fossils of the Paleozoic era and lived in the sea. They were kings of the seas for 300 million years until they became extinct at the end of this era.
Well, almost all Cambrian rocks deposited in a marine environment contain trilobites. Paleontologists studying trilobites from the Cambrian hope to find common species, or at least common genera, in different parts of the world. For example, the genus Paradoxides is found here in the UK. It is found in Spain, in North America, in Morocco, in Italy, and in other parts of Europe, like Scandinavia, for instance in Norway and Sweden.
The most significant fossil to be found at this locality, at Portherau, is the giant trilobite Paradoxides davidus. And this was first found by John Salter back in 1862, when he landed at this inlet by mistake. He was going by boat around the coast of Pembrokeshire, looking at the Cambrian rocks here. He meant to land at Solva Harbour, a short distance to the east, but instead landed here at Portherau. He began looking at the rocks, and quite quickly he found examples of this giant trilobite here, up to about 30 centimetres long. At that time, it was one of the largest trilobites known from anywhere in the world. We have a nice example here from the collections of the National Museum of Wales, collected about 25 years ago, and this shows the characters of this trilobite very well.
The first Cambrian fossil specimens found on the Welsh coast and in Sweden led to new finds in Bohemia, Montagne Noire in France, and in Spain, the Montes de Toledo area and the Aragonese section of the Iberian Range. The abundance of trilobites and brachiopods gave rise to the expression primordial fauna, as they were considered to be the oldest signs of animal life on the planet. Excellent examples of this primordial fauna can be found in the basement of the National Museum of Wales in Cardiff. This is material of extremely high scientific value, and it has been rigorously classified. It is still being studied and continues to provide clues to the many mysteries that are yet to be solved. The Cambrian seas were not only populated by trilobites, although theirs is the most widely extended image. The seabed was teeming with unusual animals and plants. We mainly know of their existence thanks to a score of sites that have produced exceptionally preserved fossils. 100 years ago, the American paleontologist Charles Walcott discovered the first and most impressive of these sites and key to understanding what life was like during the Cambrian period: the Burgess Shale in the Canadian Rocky Mountains.
Most of the fossil record is made up of the hard parts of organisms, their shells and later on bones and teeth. But we have several localities in the Cambrian which are exceptional because they preserve not just hard parts but also the soft tissues. So we get other organisms like worms and jellyfish preserved in the record. The Burgess Shale was one of the first localities. It's in Western Canada. It's about 510 million years old, where this kind of work was done. And it has a remarkably diverse fauna that shows where all these different groups appeared. Nowadays, people are looking still at Burgess Shale, but also at several other important localities. The Cheng Jiang locality in China is somewhat older, about 525 million years old. And there are also important localities in Australia, at Emu Bay, and in Greenland. And here in Spain, there's also a locality with soft part preservation in the Cambrian at Modero.
The Sedgwick Museum at the University of Cambridge in Britain has one of the best collections of Cambrian fossils from the Burgess Shale. This result was brought about by the ongoing activity of British researchers who have been involved in the study of the site since the end of the 1960s. After the 65,000 pieces held at the Smithsonian Institution in Washington and the magnificent collection at the Royal Ontario Museum, this is said to be the largest collection of Burgess Shale fossils. These collections are the base for the book by paleontologist Stephen Jay Gould, titled Wonderful Life. Thousands of kilometres from the Burgess Shale, another key site for understanding the Cambrian period can be found in Cheng Jiang, in the southeast of China.
The fauna of Cheng Jiang is around 530 million years old. This is the first appearance of a great variety of fossils in the history of the Earth. The findings show practically every type of animal.
On the same continent, on the banks of the river Lena in eastern Siberia, the Sinc Site, another of those exceptional locations, is to be found owing to the wealth and variety of Cambrian soft-bodied fossils found there.
Its importance lies in the fact that it's the only site of this kind in carbonate rocks. The other similar sites are found in clastic rocks. Here, some soft parts of animals, such as the mussels, are preserved, which are impossible to preserve in other places. Naturally, the soft parts are not in their natural state. They have been phosphatized. This process is only possible in carbonate rocks. This is why the Sinc Site is so interesting.
Joining this list of major sites in recent years is that of Murero, in the province of Zaragoza, in northeastern Spain. The first soft-bodied fossils appeared at the end of the 1980s, and the number of specimens has grown exponentially over successive excavation campaigns. What makes Murero unique among the world's other exceptional sites is that it presents a continuous fossil record of 10 million years. It is by far the longest duration known to researchers. The presence of soft-bodied fossils in its strata, together with other skeletal fossils, increases its interest for scientists. It speaks loudly of evolution at its peak, of a planet in effervescence, and of life's struggle to find forms to express itself.
In the context of research into Cambrian sites bearing exceptionally preserved fossils, Murero is significant in that it has the most complete geological record in the world. It spans some 10 million years. So we can study how the different marine communities developed on the continental shelf in a tropical climate during this 10 million year period. In Cambrian sites of this nature in other countries, there is only a small record of approximately 500,000 to 1 million years. Here, we can study a record in the interval between 515 and 505 million years ago. In Murero, we are always in a marine environment of a continental shelf, in a gulf that would have been connected to the ocean through what is now the Cantabrian mountain range. In this gulf, there were occasionally littoral environments, but they were predominantly sublittoral environments of a certain depth. At times, they were protected by shoal areas, and on other occasions, they were perfectly connected to the open sea, but always with the seabed at a depth ranging from a few meters at most to about 100 meters, and always on the continental shelf.
The Murero site has been recognized since 1862, when the French researcher Édouard de Verneuil described the presence of so-called primordial fauna there.
The Murero site is of great significance because of the huge diversity of fossils found in the rocks there. Not only do we find trilobites, such as we find here at Portherao, but also a huge diversity of other arthropods, some like trilobites, some less so. We find lobopods, we find a number of worm-like animals, also sponges, and brachiopods with the pedicle preserved on them. And many of these are not hard mineralised parts like the trilobites have, but comparatively soft parts.
The presence of 9 animal phyla and 2 plant divisions has been documented in the Rambla de Valdemiedes in Murero. A phylum is the primary division of the animal kingdom. Almost all of the present-day animal groups on the Earth are descended from Cambrian fauna. Magnificent specimens of arthropods, brachiopods, echinoderms, poriferans, cephalorhynchs and algae have been found. This site can be considered the Sistine Chapel of trilobites, from the number and variety of the finds.
This place is world famous for the large variety of trilobites. About 100 species have been found here alone, which is probably a world record. But apart from these skeletal fossils, as trilobites were, there are many other groups. Some of them have a skeleton, such as the brachiopods and the echinoderms, and others don't. For example, different types of worms, fossil sponges, and also the ancestors of groups as exotic as lobopods. The lobopod record in Murero is key to the understanding of the evolution of this group, which is still an enigma.
One of the determining factors in understanding the rapid evolution of trilobite species is the acquisition of more effective mechanisms in sexual reproduction. Here, in Murero, the oldest proof has been found of differentiation of animals by sex. In other words, of sexual dimorphism. Male and female individuals have been identified within the same trilobite species. They are distinguished by the shape of the thorax and the length of the tail. The female has a longer tail so as to be able to carry her newly laid eggs. Until evidence of earlier sexual activity is found, we can say that sex began in the Cambrian. Murero finds tell us that sexual dimorphism is at least 515 million years old. There is evidence of sex and life in the Murero strata, and also of death and extinction. Between the lower and middle Cambrian periods, some 510 million years ago, one of the first great animal extinctions took place in the history of the Earth. Most trilobite families disappeared as the result of major changes in climate and the chemistry of the oceans.
There was a great extinction. Some 70% of trilobite families were replaced by other groups in the Middle Cambrian. This is what is called death as the creator of life. The great extinctions of species produced voids in ecosystems which, after a more or less short geological time, favoured the appearance of new species adapted to those ecological niches that had been left free. The history of life is a series of great extinctions and large-scale evolutionary radiations. We can consider it in this way.
The history of life is undeniably one of the greatest challenges to human knowledge. Paleontology is still a young science. It is the compilation of knowledge that depends on new findings and research to come to light. The exchange of information and work groups on known sites helps fit together the pieces of this complex puzzle. International meetings are being held with increasing frequency in an attempt to update the huge flow of information coming from fieldwork and laboratories of museums, universities and research institutions. One of the latest meetings was held in Toledo, on the Iberian Plateau in Spain. Paleontologists from 4 continents gathered in the city of El Greco in the summer of 2008. The 4th International Trilobite Conference has contributed to making the site at Murero one of the benchmarks in the study of the Cambrian period. Incidentally, this small town in the Spanish province of Zaragoza has raised this fantastic animal we know as a trilobite to the level of a symbol. For years now, it has been the central figure on the town's coat of arms. It is one of only 4 places in the world where this protagonist of the Cambrian is used as a symbol for a community. It is an emotional connection with the history of life. Efforts have been multiplied, but still no definite answers have been found. Researchers continue to excavate geological strata in the hope of a find equivalent to the Rosetta Stone, which allowed Champollion to decipher Egyptian hieroglyphics and eventually to know the causes leading to the Earth being populated by animals.
Well, the question would be what that Rosetta Stone might involve. And I think the ideal deposit would be one that's closer and closer to the timing of the explosion. So we can get back to about 525 million years with these Chinese fossils. If we could get a locality at 530 or 535 million years with this kind of exceptional preservation, that would be the potential Rosetta Stone, because that would show the earlier stages, perhaps, of the process.
The thought that we are separated from our earliest biological ancestors by over 500 million years both unsettles and excites us at the same time. And perhaps it might just show us how to face the future as a species, as living organisms who have reached the surprising evolutionary level of being able to reflect on our origins.